Welcome to Stochastic Processes. This is the second of two lessons on the topic of gambler's ruin, and it's the fourth lesson overall in this series. In this lesson, we're going to talk about the expected duration of a ruin from the time of the beginning of play. In the previous lesson, we talked about the probability of ruin, and we'll need that information in order to compute the expected values. So we want to know how long does the game last on average, in other words, the expected value. And let me point to where we're at here. So in part 3, the previous lesson, we answered who eventually wins. We computed the probability of ruin for player A, and then we also showed it's possible to compute the probability of ruin for B. We now ask how many plays that it takes for the one of the two players to eventually go broke. So we introduce this variable n, the number of plays until the game ends. K is we've defined in the previous lesson. It's the number of units that A starts with, and the pot is A. So in other words, player A starts with K and player B starts with A minus K units. We want the expected number of plays given that A starts with K units. So that's this conditional expectation here. K is the number of units that A starts with, and we want to know the number of plays until either A or B is ruined and the other player wins the entire pot. And so that's N. This is the definition of expectation, conditional expectation for a discrete probability distribution. So it's just n times the probability of given k that it takes n steps to finish the game, n plays to finish the game. Okay, so we want to compute this, y sub k. We need to do a little bit of work to get there. It'll take a few slides, and then we'll set up an equation, a difference equation, just as we did in the previous lesson. Although this will be a different difference equation, and then we'll solve that and we'll get our answer for y sub k. Before computing the expected length, we should check that the question is well posed. In the last lesson, we showed that the sum of the two probabilities of ruin, this was for A and this was for B, sum to 1. So the game terminates with probability 1. Someone always goes broke. There's no intermediate case where the game goes on forever. The conditional probabilities, therefore, sum to 1, which I'm showing here, for each value of k, which is the starting number of units for A. That makes P, the conditional probability of P, given A starts with K and the game ends in n steps, a genuine probability distribution function, which we need in order to compute the expected value. So that kind of puts us on firm ground. Now let's continue with the derivation of the expected value. So this is a similar approach that we've used in the previous lesson when we computed the probability of ruin. The conditional probability of A starting with K and the game ending in n steps can be written this way using the law of total probability. This is just saying A wins the first game with probability P, and then the game finishes in n minus 1 steps, given that A now has K plus 1 units, or A loses the first game, now has K minus 1 units, and then the game has n minus 1 steps remaining to go to ruin. So we can write this as this sum here. So this is kind of leading us in the direction of getting a difference equation. So let's proceed on the next slide with that. Okay, there's a lot on this slide. Let's try to go through it slowly. y of k we defined earlier. That was just the sum of the conditional probabilities of p n given k. And I plugged in the equation here. So this was p n given k that we derived on the previous slide. So I plugged that in here. Then we had n times that. And then we make a substitution, s equals n minus 1. And so the sum goes from 0 to infinity. And we broke it into two sums. And the n, we can solve for that. It's s plus 1. So we get s plus 1 here and s plus 1 here. Then the n minus 1 is s. It's here. And what else do we have? And I think that's it. So we've just broken it into two pieces. You may want to take a minute or two to have a look at that and pause the video. But that's critical. And then this gives us a difference equation. So we have P, and then this is just here, this is y sub k plus 1. And then this is Q, and this is y sub k minus 1. Now there's one thing I kind of glossed over. The 1 here and the 1 here, when you multiply that out, you get two separate summations. So you get the sum from 0 to infinity of this, which is 1, and then same thing here. You get the second term that sums up to 1, and so you get p plus q, and that equals 1. So that's where this 1's coming from here. So in other words, each one of these summations divides into two pieces. The first piece is here, the first piece of this is here, and then you're left with just the summation over these conditional probabilities. And they each sum to 1, but then they're multiplied times q and p, and q plus p is 1. So you get this here. Okay, so quite a bit. I left off a few steps in the middle. Again, you may want to pause the video and study this a little bit, but this is the critical thing here, because we can solve this difference equation for y sub k, and that's what we're looking for. If we rearrange the terms slightly from the previous slide, we get this equation here. This minus 1 is known as the forcing term. And if you compare it to the difference equation from the previous lesson, you notice the structure of this part here on the left is exactly the same. The only difference is this forcing term that we have here. Intuitively, this minus 1 is counting the term that we conditioned on, and so we have a minus 1 here. And then we have boundary conditions. If we start with 0, the expected 0 meaning the for A, then the expected length of the game, the number of plays, is 0, and the same thing if player capital A started with A of the units, we would again have an expected length of the games, number of games, to be 0. So we have these conditions, initial conditions, or boundary conditions, I guess we should call them, and the this equation here to solve. So let's go ahead and solve that. And again, we want to find y sub k, or a formula for that. To solve our difference equation, I'm going to refer you to my book. I'll give you the reference and the information to this video. There's actually two relevant sections. One section is on stochastic processes, and then the section before it is on difference equations. And actually the solution to this particular problem is in the difference equation section. So I'll give you that information. I'm just going to quote the answer here. It comes in two parts. If you recall from the previous lesson, this is the solution to the homogeneous part. And then there is this added part because of the forcing term that we had, the minus 1. So we get this equation here. As I mentioned, P doesn't equal Q in this case. So we have R equals Q divided by P. And then we have our two boundary conditions that we mentioned previously. And if you plug those in to this equation, you're going to get C sub 1 plus C sub 2 equals 0. And then this a bit more complicated expression here. So we have two equations and two unknowns, which we can solve. And I'll show you that on the next slide. So the first equation gives us C sub 2 equals minus C sub 1. Then we substitute that into the second equation and solve. And then assemble the solution y sub k once we have our two solutions for C sub 1 and C sub 2. So we plug that all in. And that's our expected number of plays for P not equal to Q is given by this equation here. Okay, so you notice here, as we had in the previous lesson, if P equals Q, you run into a problem trying to use this here because R would be 1 in that case, and this would blow up. So we'll handle that separately. On the next slide, I want to just put in some numbers here just to give you a sense of the different lengths of time that it takes for the game to end, depending on P and K and A. I have a table here for the different expected number of plays before one of the two players goes to ruin. There's a pot of 40 units to start with. These numbers across the top are how many units A starts with, and these going down here are the probabilities that A wins a particular play. So you can see here the worst case in the table, A starts with 5 units and the probability is 0.1 of winning for A. So the game gets over pretty quickly. But then you have symmetry in this table. And down here, A has most of the chips, and B only has 5 units or chips, whatever, to start out with, and B has a probability of only 0.1 of winning. So this is where B goes to ruin. And if you notice, if you look up this way and down this way, the numbers are the same because there's a symmetry here. And in the top of the matrix or the table, it's the A that's going to ruin. It just takes longer if you give A more units to start with, but since A has this smaller probability of winning, A eventually goes and loses everything. And then on the bottom of the matrix here, it's actually B that goes to ruin. So that's why you have this 148.66 at the beginning, because it's A that has the higher probability of winning, and it's A that has a smaller number of chips, so it takes longer to eventually win against B in that case. And then the numbers go down because A is getting more and more chips, and it has a higher probability of winning. And then in the middle, we're going to compute the formula later in this lesson, but in the middle they have an even chance. So it kind of goes up here, you notice, until each player starts with 20 and has an even probability of winning on a draw. So this is the longest expected number of plays before the game gets over. And then it goes back down again because now A has a larger number of chips or units to start with. And so in going this way, it's the ruin is for B and going this direction, the ruin is for A, since A has fewer chips in this case. Okay, so the next slide is just another way of presenting this table, and I think I probably gone through most of the points I wanted to already on this slide. So if we replace P by 1 minus P and K by A minus K, the two players simply trade places. That's why the top of the table is symmetric with the bottom of the table, as I explained on the previous slide. What I have here on the right is just the graph. This was the case where P equals 0.5. Now it's actually continuous, right? So we can draw it this way. And as we saw, the the highest number of expected plays was when each player started with 20 of the units, and the probability was 0.5. And I have also the graphs for P equals 0.3 and 0.4. Even though A has a smaller probability of winning, as you give more chips to A at the beginning of the game, it takes longer and longer to finish until you hit around 35. I didn't show on the table when you're between 35 and 40, but at that point, the number of expected plays goes down, and that's because B is actually going to ruin in that case. So, for example, if you gave all 40 of the units to A at the beginning, then of course B immediately goes to ruin. But even as you hit, like, I'm not sure where this crossover is, it seems around 35. So even 36, 37, 38, and 39, it's actually B that's going to ruin. That's why these graphs are going down at the end there. Okay, so that was it for the case where P does not equal Q. We still have to look at the case where the P equals Q in terms of the formulas. I mean, I gave you the results, but I didn't do the formulas yet. So we'll do that on the next slide. So let's look at the case where we have a fair game. There's a probability 1/2 that either player wins on a particular play. This is similar to the analysis we did in the previous lesson, except we have this forcing function. So the way to typically do this is first solve the homogeneous part of the equation, and then on the second slide, after this, we'll do it for the case where you have the forcing function. So here's the equation we derived earlier, and now we have P equals Q equals 1/2. So we plug that in, then we multiply by 2, and we'll work with this equation here. So first we do the, as I say, the homogeneous part. That has a double root, right? If we put in, we have lambda squared minus 2 lambda plus 1 equals 0 in a homogeneous case. And the solution, again, this is the same problem we solved in the previous lesson. So I won't go over the details here, but it's this solution. Now that's only part of the solution. We need to deal with the forcing parameter or function, the -2. Keep in mind it's a -2 here. So let's do that on the next slide. So continuing with the solution, we're going to try a constant times k squared as a particular solution. And we plug that into our equation. If you recall from the previous slide, we had a -2 because we multiply both sides by 2. So if we plug in c times k squared here, we just get 2c. There's a lot of cancellation. I'll leave it to you if you want to double check that, but you get 2c, then equals minus 2. So C equals minus 1. And so we just get minus 1 times K squared. And then we take over our solution to the homogeneous part, and we add those two parts together. And then we use the boundary conditions, y sub 0 equals a sub 0 equals 0. And that gives us capital A equals 0. And a plus ab, little a, minus a squared. And a is 0, and you solve for b, and you get b equals a. And then we plug all that in, so this drops out. We get a here. We get our equation. Then we can test it for just the one value. We put in 20 for k. A equals 40. We get 20 times 20 is 400. And if you recall, that was the middle entry in the table a few slides back. And in fact, that's how we computed that middle row using this equation here. Okay, so that's it for the both cases now concerning our problem. We did the P not equal to Q, and then we just did P equals to Q. In summary from our lesson, first step conditioning gives us a difference equation. This is when we use the law of total probability on the first step. That was all the way towards the beginning of the lesson. Then the unfair game, we derived this equation for the expected number of plays before someone went broke. And then we just completed the analysis when B and A, capital B and capital A, those players have the same probability of winning. And I should have mentioned on the previous slide, hopefully you caught it, the A and B in those equations and the players A and B are not related. I think I mentioned that in the previous lesson too, but hopefully that didn't throw anyone off. I could have used different attributes, but I just used the first two letters. And let's see, a balanced game, yeah, I mentioned this also. So the longest is 400 plays. And that's when each player has probability of 1/2 winning in a particular play, and they each have half of the pot. And this would hold true if the total, pot was instead of 40, it was 100. You would still have, the largest expected number of plays when you split 50-50 in that case. Okay, then coming up in the next lesson, which would be lesson number 5 in this series, we talk about random walks in general, drop the barriers, and walk on all integers. So this is where you can kind of just drift off into infinity. We compute the chance of ever returning to the starting point and the parity pattern in the steps. First returns. If you remember from earlier lessons, we computed the probability of starting in a state and returning to that state in n steps. But I mentioned then that did not exclude the probability or the possibility of entering that state several times before you return to it in step n. But there's another calculation when you want to actually know when is the first time that you come back to a particular state, given that you started in a state. So that's a little bit more of a complex computation, and we'll do that. Then we'll mention walks in 2 or more dimensions where the answer changes character. Okay, so this lesson is kind of a step up in terms of complexity from what we've been doing so far. And as I mentioned earlier in this lesson, in the information, I'll give you a link to my book of which these lessons are based on. It's the section on stochastic processes. And then that section occasionally points back to the previous section on difference equations. So if you wanted to get a little more background on that, you might want to read that section also. Okay, and again, don't forget to give this a thumbs up if you like the lesson.